All right, welcome everybody. This is Fred Schamberg, and today's Sendo Reliability webinar is comes to you via a comment a couple of months ago, actually, and just earlier or late last week, I also got a question very much related to this topic. It seems to be on a few people's minds, so they thought, well, let me expand this and talk about it. And the basic idea was that the question of a few months ago was based on, you know, we do a lot of testing. It was somebody that was working in an organization and had a test facility, and they were doing all kinds of different product testing, environmental testing, life testing, and stuff like that. And they had heard a couple of podcasts and other things where we talked about, well, you really need to influence the design side of things. And so they asked the question, well, we're doing all the testing, isn't that enough? And I've heard that in a couple of different ways over the years. So I thought I'd take a chance to chat about this a bit in a bit more detail. Now, testing is great, right? We learn things from it. Think of any scientific method is usually you create a hypothesis, this is what you think is going to happen, and then you go do an experiment to confirm or deny that that's what you saw. And there's all kinds of rules and ideas and stuff that you have convincing evidence from your test data. Yet it can run from very, very simple, let's just try it and play with it, to, like, years ago, my oldest was in a science competition in the community at a local science museum, and the opening challenge was being presented to a whole raft of people. The whole auditorium was full, and they had a carpeted surface that went from horizontal and went up an arc to vertical. And the idea was you needed to create a device, and it had certain parameters and size restrictions and stuff that could get to the top of that ramp. And one of the ideas struck the team that my son was a member of and said, I wonder if Velcro would stick to that carpet. And it so happened that my daughter was sitting there and she had little tennis shoes on that had Velcro straps. So they grabbed one of her shoes and ran up and stuck it on the carpet, and they had an idea. And their hypothesis is, well, would that work? And so they went and tried it. They tested it. And they then said, oh, this might just work. And so they ran with that idea, and many, many iterations and more experiments after that finally figured out a way to make it work altogether. But testing is a natural process of engineering. Is, will this support this weight? Will this withstand this set of environmental conditions? Will this last long enough? How many times can we push this button? All those kinds of questions are oftentimes answered through testing. And there's nothing technically wrong with that. But let me get into it a little more. We design in reliability. The decisions that are made during the design process is what creates the reliability performance, right? If we decide to use the absolute cheapest materials, cheapest manufacturing processes, don't worry about tolerancing, and just kind of hope it all works, we'll end up with something that might function. It might function just for a short amount of time. It might not function at all. It's kind of chance that we get something that works. If we think through, well, this needs to work more than once, or it needs to actually work over some set of conditions and time, now we're doing engineering that's related to reliability engineering. We're making decisions based on how long this device or item is going to last. So even if we don't have a reliability program and nobody knows how to spell reliability in the organization, we don't have a reliability objective or goal, most engineers I've ever worked with, most designing teams I've worked with, understand that their product needs to work and work over time. Now, there are exceptions, and I think many of you probably have run into one or more of those. But the idea is that we tend to design something that will work over time. Well, that's the reliability aspect of it. Now, oftentimes we get involved in order to, improve the odds of actually achieving our reliability objectives and do it in an economical or efficient way. And so but the design happens with or without a reliability professional looking over their shoulder or doing testing. It will have a reliability performance one way or the other. And doing it deliberately is a common technique that many of us in this audience anyway understand, that we need to design in reliability rather than just test in reliability. I think that's fairly well understood. Although, as I mentioned earlier, is this few comments and conversations I've had is that I'm not really sure that that message is clear. But we'll talk about it. Now, we do all kinds of different kinds of tests, in different industries and so on. And some are more exciting than others. Yet, if you're going to run a test, it should add value. It needs to actually provide some information that was worth the expense of conducting the test. Now, some tests are run real quick and it doesn't cost us much of anything. We do it on our benchtop, or we have a circuit board and we check a voltage on a particular trace. Those kinds of tests are almost free. And so we get a little bit of information. Sometimes we get really good information that way. But other times, like a car crash like this, is that there's probably instruments all over these things, and there's high-speed cameras looking at it. There's all kinds of stuff that they're looking for after the fact. They start taking it apart to see if it performed the way they wanted it to perform in such an incident. And I remember reading about Boeing had the new composite material wing, and the testing they did for that. And they were surprised that their modeling and so on was too conservative. It had much more robustness than they expected. At that point, they didn't change the design, yet they learned a lot about their models and so on. So there's all kinds of things to think about when you go about doing a test. But is it necessary? And so this is one of those questions to you: is testing necessary? Do you have to do it? Is it written down somewhere that it's required? And one way to look at it is that it provides information in an efficient way, right? I can run this test and it doesn't cost me a ton and I get good information out of it. Well, then it's a practical approach. In other cases, like that Boeing aircraft wing, they didn't make 40 of these and go test them to failure. They made one, and they only made one side of the one half of a wing structure, just the left side, or port side, I should say. And they tested it to failure. They didn't make a whole pile of them. If like consumer products that don't cost a whole lot, we can make a dozen or more, or a couple of hundred of them. When I was at HP making inkjet printers, we'd make hundreds of these things. And then we go off and do it. It's a path towards information, and there may well be other paths for information. And yeah, Michael, sometimes its testing is required in the contract. I get that. Yet, is it there for an appropriate reason? Is it the appropriate way to get the information that's required? Is it test and nobody ever looks at it again? Is it something that somebody evaluates and writes a nice report and then it gathers dust if it ever even gets printed? So I've seen way too many times where testing is being done as much because that's the way we always do it, or it's in the contract. But if you ran that test in the contract and nobody needs to use it, was it necessary? Was it actually useful? Now, you might get paid for writing that report, but did it affect the design? Did it affect the purchase decision? Did it change anything to add value? Maybe, maybe not. Andy's mentioned that, we do it to validate the design model. And that's kind of what Boeing was doing. They did one and got gads of data information out of it, yet it was to compare to their modeling that they were doing. What is what you're mentioning? Yeah, there's a lot of things in the contracts not necessary. I get you there, Michael. And sometimes, yeah, we know for certain, although, there's sampling error and confidence tries to get a little bit towards that. What I don't like about testing so that it works is that there's always this lingering feeling in the back of my head that goes, are we testing the right thing or the right way or with the appropriate stresses? Is early on in my career, as we were getting ready to launch a product. It was back with inkjet printers, and we did all kinds of different things to understand it, to characterize it, to model it, to do all this kind of stuff. And we thought we were in pretty good shape. And my colleague said, all right, well, in another couple of weeks, we'll know whether we got it right or not. I said, what do you mean? He says, we're just guessing at what we should be evaluating and testing. We did FMEAs, we did all these other stuff to try to narrow down what's important and what's not important. Yet, he said, in my experience, we always miss something and we get surprised. And he told me a handful of stories about previous products that it was just not on the radar at all. And so that particular test wasn't done, which would have avoided a major field problem. Well, some products are better than others, yet that's always been nagging at me, is that we only learn what we design to learn when we do testing. Now, HALT is, kind of the free form, go figure out what fails, yet even that won't catch everything. And so there's always this piece of me that's saying, we got to do more than just testing. And what testing we do has to be actually valuable, actually add value. And we'll come back and talk about that some more. Let's see. Yeah, and sometimes we do testing for warranty claims. I get that, Robert. Yet sometimes we have so much information other than running a test that we already have a really good idea. There's company after company after company has finance groups set the warranty accruals and make adjustments as they go. And they're actually relatively accurate at setting their accruals to accommodate field problems. And more so in companies that have families of products and they have, little iterations from one design to the next and so on. So maybe a 5% of the product changes from one version to the next. They have tons of real data of warranty claims, which is way more accurate at predicting future warranty claims. Now, of course, there's plenty of exceptions where there's some class defect or there's a problem with supply chain or manufacturing or inherent in the design that throws a wrench in that. Yet by and large, the finance team really doesn't need the engineering information to estimate warranties and warranty expenses. They're doing pretty good all by themselves. And so I don't really believe it's necessary. It might be the appropriate path in a particular situation. Let's see, Max talking about, I think Robert's saying, is where my organization struggles if we want some sort of show of confidence to confirm the design. Well, I know Chris Jackson often talks about is that a whole lot of that is, all of us know how to set up a test that is guaranteed to pass. We could set up a test, and as long as it powers up with the lightest of touch and it just works, we could create all kinds of tests that will show that it works. That's easy. Is that of value, though? Does it actually make a difference in one regard or another? Yeah. Yeah, I agree. Contracts, regulatory organizations require it. I don't know that it's well understood around the world of all of the various problems with doing testing. I know this audience does. for maintenance purposes necessarily. That's an interesting idea. You know, I know that when I'm, you know, in a factory and we're putting equipment back together, replaced a bearing or a motor or something like that, there's often a checkout. You know, was it assembled correctly? Did we put it all back together? And that's an appropriate test to make sure before you create more damage in the line. Yeah, you know, one of the things with Robert, with doing a test on a full product for a 3-year warranty, you know, or claim that it would last 3 years, is, well, what mechanism are you going to use? Are you going to test it in real time? Now, that becomes problematic when it's a 24/7 type operation of a piece of equipment, because then you got to run at least 3 years and maybe longer to have reasonable information. As soon as you start doing accelerants, is then you're in that competing failure mechanism mode. And are you accelerating all of the mechanisms equally? I press that it's difficult, if not impossible, to do that. And most electromechanical type products that we produce these days, that temperature accelerates different mechanisms at different rates. Same temperature, same product, all kinds of different mechanisms at play. And how do you interpret that? How do you understand if it's actually useful or not? Yeah. Ajit, I'm going to talk a little bit about the customer use case for testing, and one that went off the rails a little bit. So let me get into that a little bit. Here's some examples from my experience. So years and years ago, I was being interviewed by a major company making a little handheld communication device. I'll leave it at that. And some of you I know have heard this story before. And I was there at 8:00. I was met in the lobby by the hiring manager. We went into a small conference room, and one of the first questions was, after getting some coffee, the first question was, so if I hire you, what will you do to help us achieve our reliability objectives? And I quickly drew a flow chart and said, you know, at these different stages of this, I'd be working with the design team to make sure that we're designing in reliability and understanding where the weaknesses are and where we needed more information. And he said, whoa, stop right there. We're not even 30 seconds into the interview. He says, you will not be allowed to talk to the design team or the developers. He says, then, well, I don't want to take up your time or the rest of your team's time for an interview for a position that I certainly won't accept, because in my estimation, if you want to achieve a reliable product, you need to design it in. And having somebody that understands reliability and setting up and running the testing that would amplify their ability to design in reliability is a solid path to make it happen. And if you just want me to be a lab rat and run a bunch of tests, well, then I'm not interested, and I highly suspect you will not be successful. And I got up and left. Took one more sip of my coffee, of course. And that hiring manager was flabbergasted. He was a program manager for a complex, small handheld device that was a communications system. And turns out, long story short, about a year later when they launched this product, the screen cracked and they recalled them. They didn't ship for 2 months before they had to pull them all back in, restart. Eventually, it became successful. And eventually, the organization forced them, this team that believed they had autonomy and believed they knew what they were doing, they were required to use the internal, rather sophisticated and very well-educated reliability team, which they refused to work with early on. And they were going to hire somebody to go do testing for them. Well, I turned that one down. But if you're in an interview like that and they wanted you just to run the tests and tell them how good their product is, what would you do? And I'll ask that in a rhetorical way. Let's see what else is going on here. Yeah. Andy, we discount various failure modes we don't care about. Yeah, that's convenient, isn't it? It's like, okay, let's, some of this gets so expensive so fast. But anyway, so it's part of it is the culture of that team or that organization is what's their approach. If we're just going to go run a bunch of tests, but it not really involving influencing anybody with those tests, then I really fail to see what's the point. Why do we bother? If I go run a test and something fails and he says, well, we don't believe you. I says, okay, fine, don't believe me, but I'll see you in 6 months after the product ships and we'll see if it's true or not. And I've had one too many examples of that in my career where, well, we don't believe that you did something wrong in the testing. And I'm like, okay, fine. So another group I worked with, and I actually got called in to help them with this one, was that every time they had an issue in the field, and it was a field problem or a problem they couldn't deal with, or that caused major repairs, returns, or a spike in warranty, is they would add a test to their product lifecycle. They would figure out how to detect if this particular bug or issue or problem was there, and they would add another test. And when I got to them, they had 48 different unique tests that they were struggling to get enough samples or enough test time on any of them to be useful. And their product was a server. It was relatively expensive at the time. And it was a real pain to get the final design because they didn't want to start any testing until they finished the design. And they were getting manufacturing samples, not the prototype samples, but they were just ready to launch. And then they had to run this gauntlet of 47 different unique tests. Took months. And at that point, the design team was all kind of holding their breath, hoping that their part of the design didn't fail, because then they would be frowned upon and told to go fix their issues and their ways and so on. And they almost never had a failure during those 47 tests. And this is through 3 to 5 different product cycles that they'd gone through, and regularly adding new things to the test, to the thing. And it never really dawned on them that if you anticipate the type of problems that you're having and design them out from the start, you won't have the field problems, the customer complaints that then say, oh yeah, we should have tested for that. If you could anticipate or explore more or do other things. Plus, a handful of the tests were on technologies and failure mechanisms that didn't even exist in the product anymore. There was one for an op amp, and they didn't use op amps anymore, for example. And yet they ran a test that would detect a bad batch of op amps. And like, you don't have any in here. Why do you run this test? Oh, we always run the test. We're quick to add a test, but we're really bad at taking them off the list. Nobody ever has time to think through, why are we doing this anymore? Now that one went off the rails. That they just were going to add new tests until they just ran out of resources and time, and probably would have gone bankrupt at some point. They did have some nice features, though. Most of the engineers understood that if they failed a test, their part of the design failed one of these gauntlet running at the end of the program, they were in big trouble. And so they made sure during the design that they would pass that test. The trouble was, is they weren't trying to make things reliable for areas that they actually knew were going to be a problem. I have to pass the test. I don't need to address these things I think are risks. And by and large, it was that set of risks that they identified early in the program that ended up failing in the field and becoming a new test form eventually. But they didn't have time for that. And the emphasis was, you need to pass the test. And I was like, okay, this is one where testing was the only criteria, the final gauntlet before you could get to shipping the products. It was about as bad of an example I'd ever seen. It was amazing. Let's see. Yeah, please, Andy, don't use MTBF. Oh, that's a whole nother. Yeah, it's a bad word. It's just you should stop that and encourage your team not to. I'll talk to me offline. I'll send you a bunch of webinars on why and websites and stuff like that. Demonstration tests. Yeah, there's all kinds of ways that we evaluate units in testing. If what we're doing actually helps somebody make a difference and adds information they didn't otherwise have, and it was necessary for that program to move forward, to that design to get locked down, to that selection of a vendor, I really ask, why do we do it? What's the point? And we'll talk about that again. Ran into another group that the only testing they would do was with standards. It says, if it's not a standard, we're not going to do it. And he says, well, you have a problem with this and your design is unique. There's no standard for this. Well, we think this is a close enough standard, so we're going to do that. And they ran all these tests. They passed all these standards. They were able to list all kinds of stuff on their data sheet of all these ISO and IEC and ANSI and all these other tests that they passed. Yet they never really understood why the stresses that they were using never really caused any problems. And they were very, very happy that they passed all these standard tests. They were fat, dumb, and happy. Well, I know some of you have heard this story because it was less than a month later that of the 70,000 units they shipped, 50,000 had failed. And the trouble is that their product didn't fit the failure mechanism that ended up killing the vast majority of their products wasn't covered in any of these standards. And so by limiting yourself to running tests that either you've always done or that it's a standard suite of things we do, or it's actually a standard, really limits your capability of creating useful information. Now, I also highly object to a test that doesn't create failures. Demonstration tests, run it into, for 100 hours, and if it works, you're good. Those kinds of things are fraught with assumptions that lead you to false beliefs which if you don't have a failure, how do you know that the stresses you were applying could even create a failure? We can all run a test that's so benign, anything will pass. I think one of my favorites is we put it in a chamber, we put it at 40 degrees C for 100 hours, and we pull it out and we see if it works after it cools down. Okay, great. Why? Why are you doing that? Well, we need to do temperature and accelerate things and make sure it works. Well, what are you accelerating? Well, Arrhenius does everything, it does all kinds of cool stuff. No, specifically, what is it you're expecting to fail? He says, well, and I'll use a simple example. He says, well, if we use this gear back and forth a bunch of times, we know that wears out and that we're concerned about that. But we're using the Arrhenius acceleration factor and putting it at this low temperature, and we're doing all this stuff because the grease that we're using is only rated for 50 C. So we don't want to go over that in any way. So we're going to run this. All right, great. Is the unit running when it's in the chamber? Oh, no, that was too difficult. We're just counting on Arrhenius to take care of it for us. Right. So you have a wear mechanism when it's being used, and you're using a benign temperature, and you're not even powering the system on or running it. So what exactly is it you're trying to do here? And it just went round and round and round to where they ended up pretty much creating a test that was incapable of giving them any information. And those are frustrating moments, let me tell you. Yeah. Oh, yeah, Sebastian, that's great. I've heard that. Yeah, I'd like a quarter for it because it's frustrating. It's put it and see what happens. See if it survives. Put it in the chamber. And there's way too many of those kinds of things. Yeah, no, it's just amazing to me. Yeah, lots of assumptions. And it's not just the Arrhenius equation, Maximilian. It's any kinds of stresses we apply. In the real world, all of these stresses come as they will in various conditions and various combinations, and different situations and points in its use profile. And in the lab, we often isolate them. Well, it's really difficult to get a chamber to do vibration and temperature and humidity, because the humidity oftentimes destroys the other parts of that chamber. So it's really hard to do that. Yet when I go to the coast and get on a boat, it's got vibration, it's got salt fog, it's got temperature swings, it's got all these things all at once. And it's really hard to replicate that in a lab. It's possible, it's just difficult. So there's plenty of other examples, and I'm seeing a couple of them come in there. Yeah, 8588. Yeah, exactly, David. Yeah, I could pull up a half dozen of these things. 8585. The question I usually ask is, so what failure mechanism are you expecting this condition to do anything about? And usually then tell the story of where the original use of 8585 came from, way back when we were first putting epoxy on electronics and getting them out of metal cans. And they're so standard chambers that do this, that it's a chamber looking for a reason to exist. And we put it in there, nothing fails, or we find something and it's considered irrelevant or whatever. It just is mind-boggling to me. But assumptions, or let's just try it, let's not think through this too hard, let's hope it passes, let's design it so it does pass so our customer's happy, on and on and on. There's plenty of examples where testing is done really haphazardly or without thinking too much. And that's where the value just dissipates tremendously from whether it can be useful or not. So as you've heard me say before, and many of the other times, is we need to design in reliability. Now, I'm not going to go through all the stuff that Carl and I wrote in our book, The Process of Reliability Engineering, but the basic idea is it starts with what you're trying to achieve, right? Whether there's a reliability plan or not, the program should have an idea that this product needs to have a high survival rate over some period of time. And stated in a clear, unambiguous way, maybe break it down into a block diagram so that the different subsystems of the system or of the product will have a goal. This should be common sense, and I'm not going to dwell on it a whole lot, but the idea is to start with what you're trying to achieve and create a framework for that design team to actually then make decisions, make comparisons, understand where they may be at risk or maybe not at risk. I think I used the story of working with a computer team once and creating just a very simple block diagram and saying, all right, how reliable do each of these components need to be for us to achieve the system one? And we did a very simple, multiply the reliabilities together and there's your system reliability. Took us 10 seconds to put together a spreadsheet that could do the calculation for us. But nobody really understood the idea of apportionment and using their other insight. All right, fine. We'll just use a straight line. There's 5 components, and I use this example because I can remember the numbers. We want to achieve a 95% reliable over 2 years. All right, so we have 5 major subsystems identified here. Let's make them each 99% reliable, and we'll roughly get 95 as a system. And we did the quick math and made modest adjustment to it, and we got to our goal. Well, at that point, the power supply team just threw up their hands and says, we'll never achieve that. We've never been that good. All of our field data and all the issues we have say that, we're maybe at 97%, not 99. All right, great. We'll put 97 in there, and then everybody else has to get better. And we iterated that as the information became more and more available. The only team that really kept quiet was the keyboard and mouse group from this computer. They were sitting there going, I think we've had 2 failures reported to us over the last 15 years of making millions of these units. And that was because somebody sat on the keyboard and it broke. But the keys worked. They weren't using butterfly keys. Everything, the cables worked, their mouse worked. They had LEDs that lasted long enough that nobody cared if they worked or not anymore. After they failed, they were fat, dumb, and happy, and they figured they were 5 nines reliable. And there was nothing they needed to do, which was true. The entire program, they did not improve the reliability of their thing. They said, no, we're good. Power supply team struggled for most of the program, but they should struggle because they were the one limiting the overall system reliability. Yet that simple model allowed that team to actually focus attention on the vital few things that needed attention and actually make those improvements. There was no testing involved in this simple structure to help people make priority decisions, to make risk assessments, to make comparisons, and so on. Just the goal and the model with the development team. Right. The other part that we can do, again, without testing, is that if you're in an organization that's it's safety critical in aspects of it, well, have a safety policy. Is these areas need to have this level of safety and backup and fail-safe practices, and other parts need to have less margin and so on. The attachment of the wing structure on that airplane had better be a whole lot more robust and have more margin than that flip down tray on my seat. If that fails, it's inconvenient. If the wing fails, that's a problem. And so create guidelines and policies and safety systems that give a clear guidance to the team of what works and what doesn't work, and where they cross boundaries. Where do you get close to things that we need to focus on or evaluate or whatever? The other part is best practices. Let's not repeat mistakes that we've had. Let's not wait until we're testing it to realize that, if we put these capacitors too close to the screws, they're likely to crack. So let's not put them there. Let's just create a rule in our layout practice, or layout software, that keeps it away. If we need to repair something, we put keep outs around it, and so on. Let's create the range of what we've learned the hard way or what we've learned from industry, and then just make that part of the systems we're using to design a product. Now, sometimes these are not built into the CAD or to the layout software we're using, but they may be, considerations. When I was at HP, our internal guidelines often included kind of best practices, combination of performance and its durability. For different circumstances, we'd use a particular class of capacitor. We didn't need to relearn this because it was part of the documentation that everybody had. And we spent a lot of time doing education across the corporation to keep the awareness of why those practices were there, why those policies were there, and how to use them. So a lot of what we did was based on capturing what we already knew and making it visible. And I've talked about really good lessons learned type systems in the past. This should not be new to you, especially this audience. The other thing is what Chris Jackson often talks about, and Carl talks about, is that you really need to focus on the vital few. We really don't need to run the entire system to understand that the power supply is the critical life-limiting part of our system. We probably already know that, and I'm using that as a simple example. But if we know that we have something that either we don't know if it will last long enough or not, or that it's a perennial, the life-limiting object of our system, well, let's focus on that. Focusing on the keyboard really isn't going to get us anywhere. Putting any resources into improving the keyboard is really not going to help improve this one area that's critical. Like, I'm going to use power supply as my pet part of the project that usually limits the life of an electronics box. But the idea is that if we can put our scarce resources towards the areas that the design team says, hey, we need information on this. This is uncertain to us. This is unclear. Either we don't know how it's going to fail. Well, there's a candidate for halt, right? Or we know what the failure mechanism is, but we're not sure if it will last long enough in our application. well, that sounds like an accelerated test to me. Yet testing should start with that kind of genesis. It's what is it we need to learn? What decision do we have coming up that is important to the project? And let's go focus on how do we get that answer. Now, testing might be the right choice. It also might not be. There might be other venues or other paths to getting that information that is a much more efficient and informative than trying to stand up a test. And so I think you see where I'm going with this is you need to first justify the rationale or need to do a test before you even start it, before you start heading down the discussion of how many samples you need. All right. Now, I'm going to leave this as a rhetorical because there's a lot of other things we can or should do. Yet I didn't mention testing very often in that, quick overview of what we should be doing to make a product reliable. It really hinges on that the basic idea is that the design itself, all of those decisions during the design process is what establishes the reliability. No amount of testing at the end of the program is going to improve the testing or improve the reliability. We can't test it in unless the team is willing to go back to the drawing board and redesign these things that we found out. Proving that it works, that might soothe somebody's ego or help them sleep better at night. Yet, what does it really give you that you should have done much, much earlier in the program so that that test would have been irrelevant? Where is the maximum input and influence that we can have with what we do in the lab? That's kind of my main message here is it really necessary? Now, if you're in an organization that does a lot of testing and you do it just because, or just throw it in the chamber, I like that example, or it's in the contract or whatever. Well, what do you do to break that cycle, get out of that realm and start influencing the design team, actually helping that team make better decisions? Well, one of them, and this comes from all kinds of things I've been talking about for the last decade or so, which I was pleasantly surprised. I've been doing webinars since mid 2014. So I'm coming up on a 10-year anniversary of doing that, and not counting all of the ASQ webinars that we did prior to that. The idea is that if we're going to do anything in a reliability program, and testing included, it has to actually have a return on investment. It costs money, whether it's liquid nitrogen or it's a chamber or it's we're renting some equipment or diagnostic equipment, the failure analysis equipment processes. That's all an investment. Well, what do we get for that? What is the return? How useful is that information in real dollars and cents? What's the return? What is the value? If we can't determine the value of it, then it's really a question in my mind anyway, of why would we want to do it? We've got lots of other things to do with this money that we have available to design and evaluate a product or manufacture a product. Is running this test the right use of that resource? But the idea is not, oh, we'll learn something. Oh, we'll get confidence. We'll get this. Like, well, is that what that program manager really needs? What's it worth to them? How important is the decision to go to market or keep us in the lab for another month and improve the design? Let them understand what's this investment really going to provide them. So when we state value, it's in terms of the decision makers. It's the people that are going to need to use this information. The counterexample is that a company says, thou shalt do halt testing on every prototype. And then you go talk to the program manager, the director of engineering, and they say, yeah, some VP said we had to do this. And I have a stack of reports over there. And it says, well, do you use them for anything? He goes, of course not. They overstressed it and they just broke. That's a silly test. We don't condone that. Yet for years, they were running this test and they were stacking up reports that had information about 90% of the problems they had in the field, and they chose to ignore it. Well, at one point, it's like, why are they running this test? Well, they're mandated to do it. Well, if you don't use it, why even bother? He says, well, the politics inside the company, blah, 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 or it's in the contract or whatever. But what a colossal waste of resources. And on both sides. I mean, if they would have used the results and designed out these problems, they would have really impacted their field failure rate. They chose not to. Yeah, window dressing. You get a lot of that. It's, I think, one of my favorites, and I haven't told this story in a long time, is I was actually going to a fan vendor to find out why their fans were so much better than everybody else's. And the director of engineering showed me this room that was actually a big window in front of it along the hallway. And they had all their fans, all kinds of models of fans, very little itty bitty, IC cooling type systems to great big fans that would cool a large server rack or something like that. All kinds of sizes. And they all had streamers on them. They're blowing air all over the place. And I said, what's this about? And he goes, well, because you don't have any back pressure on it. You don't have any power cycling on it. You don't have anything other than they're just running. Half of them don't even need bearings anymore. Once they start spinning, they're probably just going to run forever. And he goes, yeah, that's why we put a backup power supply in here, because whenever the power goes out, it takes us a whole day to get them all going again. Okay, this is absolutely total garbage. This is window dressing. It's a nice display that you can blow streamers around, but that's about it. But that's what they used to convince themselves and their customers that their products were good, as opposed to their actual relatively low field failure rate. Their designs were actually pretty robust. And it wasn't until I got to the design team that they said, well, we want it to work. We don't want them to come back to us. And so we have the luxury of charging a bit more. And we got this reputation that we make good bearings. And so we can use better materials. We can take less risks with our designs. We don't have to cut corners. And our products just work and people pay for that. And he says, now I think I understand. It's not the testing you're doing, it's your design philosophy that actually made the difference. And so it was the window dressing comment there, Kenneth, really triggered that memory for me. It was just absolutely mind-boggling is what they were doing. The idea is that when we want to make a change, when we want to break away from testing just for testing's sake, is that we need to add value. With every discussion, encounter, proposal, anything we do, is that the other person that we're working with or interacting with has to come away with some information or insights or content or guidance that improves their lot in life, that helps them make a difference, that helps them make a better decision in their design process, helps them choose the appropriate vendor, including a bit more information than they had before, and on and on and up. And sometimes what we work with other teams is that it might not be reliability related. How do I get my prototypes faster? Was one case where I really broke the ice with the design team I was working with because I figured out a glitch in the procurement process that made the process of getting a prototype a week longer than it needed to be. And so for a very small amount of money, we were able to shave like 6 days off of the 8 days that it typically took. And it was because they didn't want to buy a stack of capacitors that they might not use. Well, a stack of capacitors for 100 prototypes was a couple $100 max. Yet it basically idled the design team for a week while we waited for prototypes to show up. And it was dramatic how much of a difference it made for one small policy change. Yeah, we can scrap these capacitors because we just saved a week, and time to market and getting prototypes back in the hand of the designers was so much more valuable. Now, does that have anything to do with reliability? No. But that team owed me because they knew I did that. They found that, made that recommendation, made that change. Now they started to encourage me to speak up more, to ask for what I needed for the reliability to improve and so on. But sometimes it takes getting outside of our lane in order to add value. And once you're seen as somebody that adds value with every interaction, with every opportunity, then you become a player, a necessary part of that team. There's a whole lot more we can talk about on that. That's probably a whole other podcast or webinar. The final thing, and this applies especially in the testing world. Why are we doing this? For everything we do, is the FMEA or HALT or a test, the 8585 is my favorite, right? Who needs this information for what decision? And that's key, because if we provide information that doesn't actually help somebody make a better decision, then that information is of little to no value, right? If we are going to provide HALT to somebody, the results of HALT testing, and they've told us they're not going to use it, well, I wouldn't even bother printing it. We might be mandated to run the test, yet I would avoid the frustration of trying to convince them if they're just dead set not going to do it. And I'd lobby back to whoever forced us to do this test to say, don't you have something better to do with these resources if this is just not going to be used? It was, I would also then look at, the correlation of all this years of running HALT and all of the correlated field problems that they had and how much that cost you, to try to convince people that it's actually worth doing. It was an interesting experiment that they ran inadvertently to show the value of HALT. And then they just steadfastly didn't want to fight the fight to make it useful, to actually get it used, which was a setback basically. But also, what exactly do you need to provide? What is the expectation of the person that needs this information that you're providing? What format, what structure, by when, all of those different aspects of it. If we're going to run a test or conduct an experiment or consume some resources, it should have a very clear, not should, it must have a very clear need for what it's trying to achieve. Now, every experiment we run isn't going to guarantee us the perfect information. And that's part of the risk taking that we're doing when we consume resources. Yet, if you don't know exactly who's going to use this, the results of the 8585 chamber and what they're expecting to learn, and how does that make a difference, well, then we're probably setting ourselves up for a process that adds little to no information. And so, a couple of thoughts here about how to go about doing this. Let's see, I think, and challenges. I wanted to have plenty of time here for challenges. Let me see what's on the chat board here. Yeah, Mike, a lot of people do that, is they connect the reliability program and quality program and marketing and all kinds of stuff to the phase gate process. We have concept and development and detailed design and go to manufacturing and so on. And there's different stages of that where we're having to report out all these different tests that we do. Did we pass this environmental test? Do we do this? Do we do that? Well, that's interesting, yet it's kind of backwards, where we're mandating that we do these different hurdles to get over. Yet the likelihood of that test result actually adding value, other than that it was done, it's a checklist kind of thing. Yeah, we did that test, we passed. Or we did that test and we think we found something, as opposed to very deliberately using those testing resources to address those vital few, the areas that are, I heard a good acronym, I think it was NUD, N-U-D, new, unique, difficult, or something like that. I don't remember the parts of it, but it's what I used to call, or usually call, red flags. It's a new vendor, it's a new application, it's a new environment, it's a new technology. Those things usually come with lots of unknowns and lots of questions. And those are usually areas where testing actually adds a lot of value, insight into how this device or technology works or doesn't work. Yet, too many organizations say, well, we need to run 85-85, and we need to do thermal cycling, and we need to do vibration, and we need to do this. And all of those things happen, and you may or may not learn anything. Yet, was any of those things related to what you needed to know to achieve your reliability objectives? Probably not. And I heard the argument, and it didn't come up in the chat today, was, well, if we don't run the tests the same as last time, how do we make comparisons to what we did last time? How do we know if we're making improvements? It says, well, you're comparing against something that's irrelevant. You didn't need to run it last time, and you certainly don't need to run it today to be able to compare it what you did last time. I think you can follow my logic on this. The idea is what information do you need today, or hopefully in the next couple of weeks, so that we can go get that information for you to make a better decision. Not at a checkpoint to say, oh, we did the 15 accelerated or 15 environmental tests and nothing failed. Why did we spend all that money on that if we had a very low likelihood that anything would be a problem there? So in the risk balance type of thing, if we don't run the test, we don't know. I grant it, that's true, right? If you run the test with 2 samples and on a benign set of conditions, did you really learn anything that other than what you learned when you powered up your prototype for the first time on the benchtop? Which brings up a whole nother point, is that oftentimes in development teams, I see they only want to pay attention to stuff that's coming from the test lab, whereas they ignore all of the issues that come up from all of the prototypes that are scattered across the organization, with marketing, with software, all in through the development team. They get prototypes to check their designs. Those are actually invaluable reliability tests. Did it power on? Did it perform as expected? Did it, when the software guys complain that the power supply keeps failing, and it's not a software issue, and you choose to ignore that because it wasn't in the test lab, you're giving up invaluable information. Let's see, Robert's talking about, we use a risk-based test plan. First, we do the risk assessment, and hopefully it involves something like FMEA or what keeps you up at night or what's new in the product. There's all kinds of ways of going about doing that. And then base your tests on where the greatest risks are. Excellent. I think you could have given this presentation. That's the idea. Spend the money where it makes sense. Have a good one, Robert. Thanks for your comment and attending. Let's see. Carl's put up a few things. Let me get over to the question tab. Yeah, the process, I think you were talking about early on, that modeling, set a goal and modeling, and then use the qualitative methods for predicting and assessing product reliability. It allows us to start, focusing in on what's going to limit the life of this particular subsystem in a product or this part of the technology. There's great ways of doing that. Oh, there's a lambdatest.com one. I'll have to take a look at that. I haven't been aware of those guys. Thanks, Carl. Appreciate that. It's at lambdatest.com/learning-hub/reliability testing. Be interesting in what their take on that is. Thanks, Carl. And value testing of a product reliability involves the use of quantitative methods. Okay, talked about that already. And careful planning. And that's the part I don't get is, throw it in the chamber and see if what sticks kind of thing is, and I get this all the time with accelerated testing. Well, we're just going to put it in the chamber and heat it up, see what happens. That should accelerate it, right? I said, well, temperature is a great tool for accelerating a wide range of things. Yet, if it involves actually deflecting this dome button, temperature by itself is going to probably cause it to fail eventually. Yet, if you want to know how many times can you push this button, before it cracks, you might actually have to push the button, kind of thing. We often think of, well, we have this chamber, let's use that chamber, as opposed to, well, what's the failure mechanism we're trying to evaluate? And let's assess the types of stresses that actually apply and that we can understand the model to its use conditions. So lots of ways to go about doing it. All right, let's see. I think that's all I got. Looking for any other comments or questions and kinds of stuff. I'm going to hang on the line here. Thanks for all the comments and input and stuff throughout. Appreciate that. Andy's going with focus on new and or novel components and designs. One of the easiest ways to get at that is to talk to the development teams. What areas are making trade-offs difficult, or what areas have scant information that you need to, better insights in? What keeps you up at night? All those kinds of things. Those are all great questions to get after. What are those critical few things that we really should have paid attention to? Or as a more formal risk assessment type thing. There's lots of techniques for doing that. Well, you're welcome, Mike and David. Yeah. And you're right, Nesri. We don't know all the failure modes. We do probably know all the failure modes. Those are the opposite of all of the requirements for the product. This green light should come on when I press this button. Well, the failure mode is that light doesn't come on. But why? What's the failure mechanisms involved with that? And there can be many of those. That's where this engineering judgment and understanding of our products and technologies comes into play. And thanks, Andy. Glad you got a copy of the book, started using it. Appreciate it. Let us know how it all works out. All right, now let's see if I can find my button to turn off the recording. I'll stay on the line after the recording stops if there's anything else. And thanks once again for attending.